Welcome everybody. It's a pleasure to have Vishal Baibhav visiting us for the seminar. So first of all, thanks to Vishal to give the seminar at such short notice. Unfortunately, like Subo had COVID, and Subo will give one of the next seminars. Vishal did his undergrad in India at IIT Guwahati, and then then he did his PhD at U Mississippi and Johns Hopkins with Emmanuel Berti. He's now a Sierra postdoctoral fellow at Northwestern, working with Vicky Calavera and a research group. And he's an expert on many things related to gravitational waves, in particular population analysis of gravitational waves. And today we'll talk about dancing with black holes, spin secrets of merging binaries.
Thank you so much, Jay. It's a pleasure to be here. So in general, I work on gravitational wave astrophysics, and this is what I'll be mostly talking about today. But I also work on tests of GR, some modified gravity, effective one-body theories. So if that interests you, you can just chat with me. So LIGO Virgo has detected like almost 90 mergers which involve black holes and neutron stars, but they only detect like a fraction of a second of like their millions or billions of their lifetime. So the question that won't let me sleep at night is so these black holes, most of them, they were stars at one point, like unless there are primordial black holes. So they were stars at one point. So what kind of lives did they live? So what kind of deaths did they have? What kind of supernova did they die in? And what is forcing these binaries, these black holes to merge? So you can kind of divide the community in kind of two kinds of thoughts. So the one possibility is, so you have binary stars. They are born together, they will die together, they will become black holes, and eventually they will merge, and LIGO might be able to see that. The other possibility is, so you have 10 stellar clusters, millions of stars. These different black holes are born in different parts of the cluster, but they all sink to the core where they eventually interact with other black holes and stars, and eventually they merge. So the question is, where are these black holes that LIGO is detecting they're coming from? Now, the clues to this mystery lies in these like 4 gravitational wave observables: the masses, the spins, the redshift, and the eccentricity. And of course, based on the title, my favorite one is, of course, the spins, because like they are the cleanest indicator, in my opinion, if you want to tell what the formation scenario is. So here's more like here's the outline. So first, we will look at the isolated binary formation scenario. In this case, I will discuss what the traditional thought is and why it might be wrong. And if it's wrong, what are the other possibilities, what we can learn from the black holes that LIGO is detecting, what we can learn from young pulsars and binaries, or black holes in LMXPs. Then I will talk about mergers in stellar clusters. In particular, I will talk about like the repeated mergers and what kind of spin signatures they have. So as I mentioned earlier, the question that does not let me sleep is, where are the LIGO binaries? Where are the LIGO black holes they come from? And like I said, the cleanest way to figure out the formation channel is we look at their spins. If you have black holes that are born in the field, they should have spins mostly in the same direction. On the other hand, if you have black holes that originate in the cluster, they should have spins all over the place. They should have more or less an isotropic spin distribution. So this is more like the traditional picture. What I'm going to argue is like, this is not the case. So this traditional picture where the fact that isolated binaries, they're always assumed to have aligned spins, might not be as robust as we've been thinking for almost a decade now. So first of all, where is this picture coming from? In general, you have binary stars, they have aligned spins. So when they die, they should, if they retain their spins, the black hole should also be spinning in the same direction, right? So like there are two assumptions that are going on here. So the first assumption is that the binary stars, they have aligned spins. So first of all, this is not always the case. So there was this banana project which kind of started in late 2000s. And like there have been 6 papers as of now. And this is my favorite acronym in astrophysics. It stands for binaries are not always neatly aligned. So yes, there are binaries which have aligned spins, but there are also solar binaries which have spins kind of like this. So which have almost in-plane spins.
That answer must depend on the period of the binary. So what range of periods are you talking
I
about?
do not remember actually, so I'll need to check. I do not remember. Okay, so the second part,
This plot is an individual system. So
yes, these are individual systems. So this is from the latest paper from 2021, and where they looked at, I think, around 70 or 80 different binary stars.
Is it main sequence?
Yes, these are all main sequence. These are all very like low mass. They will never become black holes or neutron stars, but like it just gives us some idea. So the second part is when they die, they become black holes and neutron stars. What kind of spins do they have? And if we look at some of the young pulsars in binaries or even LMXPs, we find that these spins, they are not aligned. They're almost kind of in most of these cases. So the question is, if black holes, they do not get their spins from their parent stars, where do they get their spins from? So one possibility is, okay, so if they do not have aligned spins, what are the other possibilities? The first possibility is that this spin direction can be completely isotropic. So this could happen because of, let's say, internal gravity waves. So there have been a few papers. So for example, the first paper was by Fuller in 2014, and then also a follow-up paper by Lucy McNeil, where what they studies was they looked at internal gravity waves, which were kind of being generated due to convective layers. And these internal gravity waves, they were transporting some angular momentum to the core or the protoneutron star in this case. And in this case, what you would get is like it would be a completely random Hawk process, and you should get an isotropic spin in this case. The other possibility is you can have, so there were these papers where they looked at the direct collapse, and in this case, if you accrete some of the convective layers, you can also get some decent amount of spins. And I remember at least one plot where the spin magnitude was going all the way up to 0.7, which in my opinion is very, very impressive. So we might not know a lot about like the spin directions for the neutron stars at least, but one thing that we do know is that the spin directions of young pulsars, they are usually in the same direction as the natal kick that they received. And this has been known since like early 2000s. People have also tried to explain this through various hydrodynamical mechanisms. So in this case, if if the black hole and neutron stars are getting the kick somehow, getting the spin somehow because of the natal kick, what kind of tilt measures should we expect? So let's assume that the kick distribution is completely isotropic. So in that case, one would expect that the spin distribution is also going to be isotropic, but this is not the case, because in general, if you get a kick which is in the binary plane, there's a huge possibility that you disrupt the binary system. And this is why, see, so this is the histogram for the tilt. And as you increase the kick magnitude, what we see is that we do not have enough systems which have in-plane spins. If you increase the kick even further, like more than orbital velocity, we start seeing these very weird shapes because the binary orbital plane is also tilting a lot. And after some point, it tilts by at least 90 degrees. So what was earlier in plane has now become kind of aligned. So at one point, you only get in plane spins. Obviously, the next possibility is what if spins of black holes and neutron stars are perpendicular to the natal kicks. And this is something that we see often, let's say, in supernova simulations. interestingly enough, even though observations say that these spins should be parallel to the kicks, but many supernova simulations, they kind of get the opposite. So for example, this paper by Chan et al. In 2020, what they find is that this angle between the spin and the kick is kind of almost 90 degrees. And like there are other mechanisms, like such, for example, like you could have asymmetric fallback of ejecta, which could also give you spin perpendicular to the kick. And the other scenario was proposed by Finney and Scott in 1998, where let's say you have a star and the explosion does not really happen in the center of the star. In that case, the kick is kind of going to impart some spin, and it would be like a R cross V. So which means that the spin is going to be perpendicular to the kick in this case.
In the previous case, you were saying that the kick, the mechanism for the kick is the one which spins you parallel.
Yes. So this is the other possibility. We do not know which one is true.
But how could this happen?
Like the previous one or this one?
The previous one.
The previous one we do not know, honestly. So
But you said hydro simulations true.
no, mechanisms have been proposed, but I do not know of a single supernova simulation which can produce supernova in the same kick in the same direction as a spin. So I can send you some reviews by Yanka where they think what would be the reason, but not a single supernova simulation has achieved this, in my opinion. So there are simulations where even though they start with a very large tilt, over time it kind of starts decreasing. But even those supernova simulations, they were not long enough to see if they can achieve like the proper alignment. Does it make sense? Okay. Yeah, so in this case, the things will be exactly the opposite. This time, for small kicks, we do not prefer aligned or anti-aligned because anti-aligned spins, because this would mean that the kick is in plane, you might disrupt the binary. And again, you increase the kick even further, the orbital plane is also going to change a lot, and we start seeing these very interesting features. So
The ones that are getting kicks large enough to produce these big features,
yes,
they're starting off at some reasonably small semi-major axis and being kicked to some very large semi-major axis.
yes. So yes,
A highly eccentric orbit.
yeah, exactly.
So will those ones actually merge anyway?
Yes. So the important quantity in this case is not just the kick magnitude, but more like the kick to the orbital velocity ratio. So it's possible that even kick might be small, but even if the orbital velocity, even if the separation is large, you can have a similar effect.
Right, but you're giving it a kick, giving it some energy, which is a water its binding energy.
Yes, and there's a big possibility that you are going to disrupt this, and that is the reason that we see these features.
But the reason we normally talk about black holes that are pretty close to each other, we want, was it 0.2 AU for them to merge?
In those cases, we are going to need like very larger kicks. Yes,
We're going to get a very large kick, but that's going to take them to a semi-major axis, which is much bigger.
So yes, it's going to increase the semi-major axis, but not enough. So I'll show you other plots like in just 2 more slides, where we are only looking at the binaries at merge. So in the last 2 cases, we looked at mechanisms where kicks are responsible for spinning up the black hole, either perpendicular to it or either parallel to it. And in this case, one can expect that the spin magnitude should be proportional to the kick in this way. And in general, what we expect is that the heavy black holes, they should receive smaller kicks. On the other hand, smaller black holes should receive larger kicks. This would also imply that the heavy black holes should have larger spin magnitudes, which is the blue color, and the other way around. So the heavy black holes should have smaller kicks and spins, which is the yellow line. On the other hand, lighter ones should have larger kicks and spin magnitudes as well. Let's look at the spin test. Now, these are the plots that you were talking about. In this case, let's look at different detailed distribution for different cases. So this is like the PDF for different masses. The yellow is like the 20 solar mass, the blue is around 5 solar masses. So in general, lighter black holes, they first receive larger kicks, which means that the binary orbital plane is going to tilt more. And also, since they are lighter, they're also easier to tilt. So that's why you will see that they have longer tails towards, they have larger misalignments. The isotropic distribution is boring, it's flat. If you have spins perpendicular to the kicks, in this case, the slightly disfavored aligned and anti-aligned binary black holes. And if you have spins parallel to the kicks, opposite is going to be true. We can also look at the chi-effective. So chi-effective is basically the weighted combination of these spins along the orbital angular momentum. So in this case, if you have the natal spins, if all the spins they come from the stars, you should have mostly positive chi-effective, which means that spins are kind of like this. But since they are getting some kicks, they should also have tails into negative chi-effective regions. So lighter black holes, they are going to they will be tilted more because they are lighter, and also because they also have larger kicks. So that's why you will see that the small masses, they have longer tails into the negative chi-effective region. On the other hand, the fact that we see that lighter black holes, they have larger kicks should also be evident in the fact that you would expect a correlation between the mass and the chi-effective distribution in this case. So as of now,
in order to make this plot, you had to assume some size of kicks.
Yeah, so we assume like 265 kilometer per second, and then you kind of scale this by the mass of the black
For
hole.
what mass? For no mass, you assume that.
Yes, so if it was, let's say, 1.4 solar mass something, it would get 265 kilometer per second. And then you kind of scale this by the black hole mass.
Just linear.
Like 1/n. So this is, yeah.
You know.
Yes. So what this means is, as of now, the general thought was that if you have, if LIGO detects something which has negative chi-effective, either it has large misalignments or whether it's precessing, it has to come from the dynamical channel.
Sorry, again,
Yes.
you assume the 265, but in order to do this calculation, you also have to assume some period in which how separated the binaries were when they received this.
Yes, so so we start with some log uniform in separation, and then kind of we evolve. Does that answer your question?
Yes.
Yes, so in this case, what was I? So yeah, what I'm trying to say is that earlier it was believed that the only clusters can produce large spin orbitals or precessing binaries or negative chi-effective. What we are trying to say is that dense stellar clusters do not have monopoly over sources like this. And LIGO has already detected sources which have either very large precession or which have negative chi-effective. So, and they have been claimed to be exclusively from the dynamical, they have been claimed to have an exclusive dynamical origin. So let's look at them one by one. So first we'll look at GW191109. So this is a case where at least the primary black hole has almost been like this. Now, in general, if black holes get all their spins from their stars, this is very, very hard to produce. On the other hand, if you have either of, let's assume, if you have spins parallel to the kicks, in this case, you can produce mergers like this even with very, very small kicks. On the other hand, if you wanted like the traditional picture to explain this, you would need a relatively larger kick magnitude to explain such tips like this.
How are these diagrams being created?
What calculation has gone into producing these curves?
So what we're doing is we take the tilt measurement from this event, the LIGO criteria, and then we have the likelihoods based on like these calculations. No, not even these, more like based on this. So for every K to orbital velocity ratio, you can kind of produce histograms of the tilt, right?
It's like there are like mass transfer can happen after the T or something.
So in the plots I'm going to show today, we do not account for mass transfer or drives, but we are writing a paper where we also kind of see if you allow for mass transfer or if you allow for tides, how would these signatures change? And we are even allowing, let's say, in this case, I assume that this spin is exclusively coming either from its parent or from, let's say, it's being spun up parallel to the kick. But we can have a combination of both. And in these cases, the picture is going to change slightly. So yes, these factors are important, and they're also going to have an observable effect on the tilt distribution.
So these kicks are coming from the supernova, right? The
Yes.
asymmetric, if
Yes.
there is an asymmetric supernova, you will kick to conserve linear momentum. So why would that be correlated with the spin?
So they are, okay, so we do not know, you're right, we do not know for sure if it would be correlated. What we want to see, are they correlated? So the two reasons people think that they should be correlated is if we look at young pulsars, they usually have kick and spin in the same directions. So that is reason one. And then there are, we
Why
do
is
not
that?
know.
Okay.
We do not know. And then the second one is there are few supernova simulation and few, there have been other theories which predict kick and spin to be perpendicular to each other. So let me go back to. So in this case, so for example, if you want spin perpendicular to the kick, you can have either off-center explosion, which was first proposed by Finney and Freud in 1998, or you can have like you can also get this due to asymmetric fallback of ejecta, which was first shown by Muller et al. In 2018. Yes.
Maybe you'll get to this later, but what about the impact of the galactic potential on this? Because like, if I remember correctly, for the spin kick alignments, they say our observation on the young pulsars, that only holds for young pulsars, because for older systems, that correlation breaks down as the things travel through the galactic potential.
Yes.
And obviously for the LIGO systems, these are
Yes.
the older systems. micro systems.
So, okay, so for pulsars at least, okay, so the pulsars at time, young pulsars and binaries, so over time, of course, they're going to accrete matter from like their partner, and they are going to get spun up because of this reason. So I'll talk about one particular system, where which this is exactly what happened. So you have, maybe I'll get, okay, yes. So where was I? Yes, so this is one scenario. The another popular event was GW190521. Now this is the one which is known for like having a very high precision. And again, in this case, normally, if you were to use the traditional picture, you would require larger kicks. On the other hand, for all the different models that we discussed, even small kicks would be more than sufficient. So now what can we, so like we just looked at two different events, what can we learn from the full population? And if you look at the traditional picture, which is like you should have isotropic contribution to the tilt, it should come entirely from the clusters, and you should have an aligned component which should come from the field binaries. In this case, this is what you should expect. And this is what LPK was doing for a long time as well. And they were trying to find stuff like what's the fraction of isotropic binaries. But like last year, people started being more flexible with their models. And what they find is that this model is not consistent with LVK observations. We get a peak at around 60 degrees in the tilt distribution. So this was first found out by Salva Vitale earlier last year, and it has been reproduced by like a bunch of other papers as well.
You mean the peak is like at one that is disfavored, but the peak is at like lower, you
Yes.
could have a two component one with the aligned peak lower 0.5.
Using this model?
Yes. The model you say is ruled out is just the center of the peak for the aligned one is at one. That's what you mean?
Yeah, but that would be very hard to that would mean like there's something special about like 60 degrees, right?
Yeah, I'm just trying to understand. When you say ruled out, what do you mean? Like it's at one, the peak at one is ruled out.
Yes. No, actually, it's not also, I'll discuss it later on. It's not exactly ruled out because this thing is still like quite prior dependent. So this first paper was kind of titled "Spin It As You Like" because they realized like this is quite sensitive to what kind of priors do you assume. And actually, if you look at this paper by Callister and Farr 2023, they actually reproduce both the peak at 60 degree and they also have another peak at 1 as well. So like this is still very interesting. This depends on what model you're assuming. On the other hand, the models that we use, it can perfectly reproduce such peaks. So in this case, earlier when we discussed, we could see like the peaks in the tilt distribution, right? And in those cases, we assume that these things were coming exclusively only from one source. But, and you had symmetry between above the orbital plane and below the orbital plane. But let's say, in addition to these spins driven by kicks, what if black holes also retain a fraction of their spin from their parents, or they're tidally spun up, or they also get spun up because of mass transfer? In these cases, you're going to suppress the peak in the below the orbital plane, and you're going to kind of get things like that, which seems quite consistent with it. So we're still working on this. So what we have is we have populations driven, like population inspired by something like this, and we are trying to see whether they can completely explain this. But like I said earlier, this is quite prior dependent. We need more data to see how robust these features are. And for this, O4 is already going on. We are going to get few hundred more events, but in the 3G or in the A+ region, we are going to reach up to thousands of, or depending on in the 3G region, we'll have up to millions of merging binary black holes, and these things will be way more defined. But before that, we can still look at what can we learn from young pulsars in binaries and black holes in low mass X-ray binaries.
So these observations are all the black hole binaries ever detected in light.
Yes.
And your model is just an isolated binary where one is going supernova, giving a cake and causing an alignment or misalignment of the spins.
Yes.
But there is also the other case where,
yes.
The
dynamical channel. Yes, we do not account for that. Yes. Yes, ideally what you should have is you should also include a cluster a cluster contribution as well. But unfortunately, what will happen is that we will not be able to differentiate between the isotropic from clusters and isotropic from the feed, which could happen because of internal gravity waves, papers by Fuller, or because of if you accrete some of the convective layers, papers by Elliott. So yes, so that kind of makes the problem slightly worse.
But assuming only one model where there are possibly two channels, won't that bias your conclusions?
Yes, it will. Yes, it will, definitely. But okay, so in this case, what I was talking about was this peak. The other channel can never produce this peak because it's supposed to be completely flat. Does it make sense?
And how robust is that prediction?
This peak?
No, it's all flat from the other channel, the dynamical.
It's mostly robust, but there are there is some other work by Fulia Kiroglu at Northwestern, where what they are doing is they are looking at you might have isotropic spins, but you could have tidal disruption. So these binary black holes, they can interact with stars, which will get tidally disrupted, and they will lead to some sort of alignment. So, but mostly it's quite robust.
You also had like some function of the kick with the mass. So you use some mass distribution from LIGO and then you do this.
No, so these are all like these different curves, they are different masses. But yes, ideally, what I am doing is kind of I'm implementing this in Poseidon, which is population synthesis code developed at Northwestern. And the idea is to see, let's say, what kind of distributions you get at the so yes, the next question is what can we learn from young pulsars and LMXPs? And I mentioned these sources, these systems early on. So what we can do is we can look at one and we can again try to find what the kick is, what the mass loss is. And in this case, again, exactly same as what we saw for the gravitational wave case. If you want to explain systems like this, using the natal spin method, you would need very, very large kicks. On the other hand, if you assume that the spins are being driven by kicks, we do not need even small kicks are going to be more than sufficient. You can do this for all the these systems. And what we find is that based on just these four systems, that the natal spin model, the fact that the black holes or neutron stars, they get all their spin from their parents, is disfavored by a base factor of around 10.
It's varied by the binary black hole population of the LIGO.
No. So what we do is we just look at these four different scenarios, four different systems, and we compare the four models that we discussed. And we cannot say which of these models is right, but what we can say is that this model is definitely disfavored just by looking at these four systems.
And the key piece of data here is
They did, yes.
So
And yes.
for the LIGO events, the natal spin model is preferred to produce that paper, right?
So no.
In this, just the previous few slides. Right?
Yes, so in this case, by itself, it's not enough. By itself, it's also not enough. We also need the contribution from spin parallel to the kicks. So it's more like you're getting these spins from multiple sources. So what probably happened is that you have a star. It did not lose all of its angular momentum and it retained some of the spin. And in addition to this, during the core collapse or supernovae, it also got spun up parallel to the kick. In that case, you can perfectly explain this. Or it got spun up parallel to the kick, and it got also got some contribution from the mass transfer, or the star also got.
So am I understanding correctly that here, in order to produce the 60-degree kick, the dominant channel is the spins parallel to kick? Is that not?
More like a mixture model. So this is not itself, it's a mixture model.
And why do you select those four pulsar systems?
So these are the only ones where we have a decent spectral measurement.
We don't have that for the other two vessels.
And yes, this is also the system I was talking about. So for example, this is I think this is for pulsar B. I should have specified this. The pulsar A, on the other hand, it's perfectly aligned with its orbital angular momentum. But this one, it's a young pulsar. But the pulsar A, it has, I think the alignment is less than 3 degrees. It's measured very, very accurately, but it's an older pulsar. It's recycled, obviously. So probably before the young pulsar formed, its parents start kind of, so the pulsar A accreted some of the matter from its parent star, and it kind of got spun up parallel to the orbital angular momentum. Okay, so just to recap, natal spin is not the only possibility which has been traditionally assumed. There are other possibilities for the spin directions that come from the isolated formation scenario as well. You can have isotropic spins being like black holes being spun up either parallel or perpendicular to the case. And this would be a natural stopping point. So if there are any questions about this. Okay, if not, I can move on. So the other possibility is for forming binary black holes that LIGO work is going to observe is in the dense stellar clusters. So you have a dense stellar cluster, millions of stars. Some of them will be heavy. They will become black holes, and everything heavy, it will kind of sink to the core of the cluster. So you have a core, a cluster core, which is almost entirely made up of black holes. Now, what we want to do is we want to form a black hole binary. In general, these different particles, they have positive energy, positive kinetic energy. What we need is something with a negative binding energy. So what happens is that you have 3 body encounters. So 3 black holes come in. And what happens in this case, the blue black hole is going to take some of the positive kinetic energy from the system. So it's going to get kicked out in this direction and leaving behind a binary pair for the blue and green black hole. The other possibility is, in addition to black holes, there are also stellar binaries in the core. And in this case, a black hole is first going to exchange with one of these pairs. So in this case, the black hole first exchanges with the orange case and before finally deciding to pair up with the blue star. This process can happen again. Another black hole will come in. It will kick out the blue star in this case. And you end up with a binary black hole pair. But these black hole binaries are still too wide to merge within the Hubble lifetime. We need to shrink them somehow. And again, the binary single interactions, they help us in this regard. So for example, in this case, you start with a very wide binary. There is an interaction, and what you end up with is another binary, which is much tighter. And this process happens over and over again till the 2 black holes, they are close enough to merge using via gravitational waves. But when they merge, they are going to receive a gravitational wave recoil. And that's because the gravitational waves, they also carry some linear momentum, which means that the black hole system and the remnant is going to get a kick in the opposite direction. And depending on the kick, depending on the spin, this kick can be very large. So this is, and it might get ejected out of the cluster. So this is the fraction of cases where you retain the black hole after the gravitational wave kick as a function of the cluster mass. And you can see, unless spins are very small, you are almost always going to eject the black holes after the cluster. But let's say if we are lucky, if somehow black holes are born without enough spin, in these cases, we might get something like repeated merger. So you have first generation black holes, which are from stars. They merge, they leave behind a remnant. And this remnant, it might decide to merge again. And like these are one of my favorite kind of black holes. And that is because like they are very easy to identify. So of course, the fact that they are born from previous mergers means that they are quite heavy, and they also have this unique characteristic spin at like 0.7. So what I'm interested in is from LBK detections, can we find out the second generation black holes? So instead of talking about what the second generation black holes can do, let's first talk about what first generation black holes cannot do. And the one thing that they cannot do or have is they cannot have arbitrarily large mass. So in general, if you start with a like very massive stars, there is a possibility that you either end up losing a lot of mass because of pulsational pair instability supernovae, so that at the end you either do not get a black hole at all, the star explodes without leaving any remnant behind, or you can have multiple pulses which eject a lot of mass, and which means that there is an upper limit on the black hole mass that you can get from the first generation. There's a upper limit on the first generation black hole mass. On the other hand, second generation black holes, they do not have such restriction, and they can start filling this gap. The event GW190521, it was like, it is known to be at least the family was around 85 solar mass. So we know that it kind of lies in the mass gap. But today we are only talking about spins. The same can happen with spins as well. So for example, let's assume that the 1G black holes, they are born with small spins, which is what is required if we want to form 2G black holes in the first place. So if you have 1G plus 1G mergers, they are confined to very small region in the chi-effective chi-p plane, where chi-effect is the black hole spin contribution along the orbital plane. On the other hand, chi-p is kind of the black hole spin contribution in the plane. So let's now add a 1G plus 2G merger. So if you have 1G plus merger, you kind of start getting this upside down banana. On the other hand, if you have a 2G plus 2G merger, you kind of start getting this like this upside down crown. And let's see where does GW190521 lie. It kind of coincides like very well with the posterior of 190521. It coincides very well with the 2G plus 2G or even 1G plus 2G region, as opposed to the 1G plus 1G.
So why are the second generation mergers giving rise to higher precision?
Because they have larger spins. Does that make sense? So if you start with, let's start with two black holes, they're not spinning at all. When they merge, they are going to get, if they have equal masses, they're going to get a spin of around 0.7. This is even if you start with non-spinning. And this is exactly what you see. So around 0.69 or something, you see the most density.
So why is it that 1G plus 1G must be spin? Assumption.
So this paper was written, it started kind of before we had an detection from PwC2 actually. And at that time, the Fuller paper was very popular, which predicted that the black holes should not be spinning at all. They were creating spins of order, black hole spins of order 0.01. And this was quite consistent with the chi-effective distribution that LIGO is seeing. It's almost like it's peaked around 0, especially after the first 10 detections. And this was also popular at that time because we need small spins if we want to have second generation mergers. So because based on this, even if you have, even if you have decent amount of spins, even very heavy globular clusters or even nuclear star clusters will not be able to retain the second generation black holes. Does that make sense? Yes, so the next thing we can try to do is, let's say we have detected a second generation merger. What can we do about this? The next thing we can do is we can try finding the properties of the black holes which led to this second generation black hole. So one example I would take is like GW190412. It was the first black hole where we were able to measure the precession. And it was also the first case where we had like very small mass ratios, where the mass ratios was not equal to 1. And like there were quite a few papers which claim like this is a second generation merger. So in this case, this is something that we observed. We observed a 30 solar mass black hole merged with an 8 solar mass black hole. And we were able to measure the spin of this black hole pretty well. Now the question is, if we trust these papers, and if this is indeed a second generation black hole, can we say something about the properties of its parents?
But isn't this like a bit fine tuned? Like for older clusters, you don't expect these unequal mass ratios mergers.
For older clusters, we do not expect this.
The lighter ones would get kicked out, like not on this. And, but like 1908-14, maybe that was like a big issue.
No, okay, actually, so this is completely reasonable. So this, for if you have something like a second generation merger, this is quite possible. In this case, actually, you would expect, so if you can see the board, right? So if this is mass ratio, this is mass ratio equal to 1, this is mass ratio equal to 0, and this is PVF. If you look at the 1G plus 1G mergers, it kind of peaks at 1. On the other hand, if you look at 2G plus 2G distribution, it kind of peaks at 0.5. So this is quite consistent. Does that make sense? So I don't think I have a lot of time. So what I'll just jump to the conclusion, and what we'll say is,
why were you focusing on this one in particular?
Okay, so because it has very well measured primary scale. So we were able to find the properties of the parents of the primary of GW190412, and what we find is that it too also likely had asymmetric masses and near zero spins. And based on this, we can also get what kind of kick the remnant might have received, so that it could have stayed within the cluster, and it probably received like very large kick magnitudes. So this means that if GW190412 was indeed a 2G merger, it must have originated from a very, very heavy cluster. And
sorry, how did you get this kick?
How did I get? Okay, so first we find the properties of the parents like mass ratio, spin magnitudes, and based on this, you can calculate the kick magnitude. Like if you have a mass ratio 0.2 spin equal to this, you can easily calculate this distribution.
Why is the mass ratio of the parent not more than 1, given that the primary 1G population is?
Yes, because if it was mass ratio 1, we would not get a spin of 0.43. We would get a spin of 0.7.
To estimate the kick, are you assuming one of your 4 models for?
No, this is different. This is different. The spins are completely isotropic, which is what we expect inside the
This is
cluster.
dynamical.
Yes, exactly.
You're just saying for it to stay within a cluster.
Yes.
The cluster this is found then.
Yes. So yes, the cluster needs to have escape velocity larger than this. If and this is very.
Do you know that 1904-12 came from a particular cluster and you're using that to estimate the kick velocity, or you're
Yes. So what I'm doing
estimating
is
the kick velocity and then using that to say something about the cluster?
Yes, the second one.
Okay.
We are estimating the kick magnitudes, and based on this, we can say like what its escape velocity would have been. And in my opinion, this is like very, very huge. So if we trust, if we trust these 2 papers, which say that this is a second generation merger, it should have originated from a very, very heavy cluster.
What about a nuclear star cluster?
Yes, exactly. So this is this kind of kick magnitude is exactly what you would expect from a nuclear star cluster. But the only problem is that the overall rate that we expect from nuclear star clusters is relatively lower, because like they are not as common as, let's say, globular clusters. So I'll just leave my takeaways here. Key takeaways here, and I think I'm kind of. Thank you so much.
Questions? I think we have a lot for them.
I'm still confused about how you estimate the kicks for the last result you were showing.
Mm-hmm.
So based just on the masses and the mass ratio,
Okay.
how does this give you a kick?
So the first thing we need so this entire corner plot, along with stuff like the spin tilts, this is entirely coming from just one measurement, which is the spin magnitude of the primary, which was like 0.43. So what this would give is, this would give us a distribution of Q, chi1, chi2, and also the tilts. And we can use these samples to calculate for each of these samples what is the kick magnitude you would expect. And that's this plot. Does that answer the question?
I guess I just, the last step of looking.
Also, this is something that we can get from yeah. So we look at numerical relativity waveforms, and we can calculate what kind of kicks they receive. So ideally, what you're doing is we are kind of doing a conservation of linear momentum. So
these are the kicks of the second generation.
Yes.
Okay, thank you. That was the process. So these are the kicks from the first generation.
Yeah.
The kicks from now. Okay.
Yeah, exactly.
Thanks.
Well, what are these two curves?
So this okay. So you mean two different?
Yeah, the two.
These are two different priors. So the blue one is the prior that we saw previously, and then the green one is the prior that we are seeing that the black holes are not. The first generation black holes are not spinning. And if they're not spinning, even in those cases, like you get very large kick magnitudes.
There was another event, this 1908-14, which was also like high mass ratio.
It was like mass ratio. Okay, so in this case, yes, we have spin equals to 0, right? 1908-14, the spin of the primary was almost 0. Yes, that can also be produced using a second generation larger, but I think it would be very, very fine-tuned and very, very unlikely.
Because of the K.
Because of the spin was I think the 95% upper limit was 0.07. So yes, you can produce actually. You can have a certain combination of the mass ratio and the spin magnitudes of the two black holes, so that you can get chi equals to 0, but that's very, very finely tuned, and in my opinion, unlikely.
So I think Vishal is here until end of today. There are a few slots. You can sign up for meetings. There's also many slots for dinner. Please feel free to sign up. And I think you will be coming back during Thanksgiving.
Probably at end of November, yes.
So yeah, you can email him and he'll be around this area.